I'm gonna talk basically about some basic statistics and application of this stuff mainly to rate items on web pages, order search results, this sort of idea. So I'm going to show some background statistics used for hypothesis testing, basically. So I'm going to introduce a bit about this. So I'm not sure whether this sounds familiar to everybody. Everybody did some statistics before. I believe so, at least. So it's going to be fairly, basic stuff, so like undergraduate level. And then I will try to, explain some more, like practical ideas behind what I'm going to show. And it's inspired by one book that I read recently, which I wish I read it at the start of my PhD rather than only recently, because some of the techniques I did use in my research, not very badly, actually, all right. So, but there are like some points that I'm going to show, and I want to conclude it with basically using the concepts like confidence intervals into ordering items for web, so like businesses, and I'm going to show some real data and all the problems with how people are doing this on the web, and also with the methods from statistics that I'm going to show. So first, to introduce, let's start from some very practical question, and I think very relevant here. Which cake to take? So that's basically the question. We have two cakes. They have some dimensions, and we need to pick one. So actually it's a good time, because we have polls functionality in our companion app, so we can use this to basically vote and see what you think, which one is bigger. But wait a second. Did you vote already?
No.
Okay, wait a second.
Can't get a connection.
Because it's not really. Let's show dimensions. Let's show actual numbers, because it's all about numbers. I think the pictures are not really. I tried to make them reasonable, but it was artificial. But look at numbers and try to tell by numbers which cake is bigger, basically. So try to think about. Like looking at those numbers, can you tell like which one is bigger? Yeah, and please don't cheat using calculators. Well, the formula is not that trivial, so yeah, just if you can. It's a trivial question, but we shall see that actually it touches like essence of the problem, really, about evaluating means. So yeah. So okay. So before, did you vote? Yeah.
Yeah.
Okay. Maybe 6 votes. So just really.
I'm voting first choice.
So okay, let's see. Because there is a formula. Yeah. So if we have those numbers, there is a formula, so we can calculate it. Yeah.
Ah, of course. This is what I was thinking of.
Well, the formula is basically, I'm thinking about this as a pi, yeah?
That makes sense now.
It's part of the circle, yeah?
Mm-hmm.
But there are problems with this. It's gonna, for real life, this is gonna be approximation only. So yeah, we have exact results using this formula. So yeah, like surprisingly, well, I don't know whether surprisingly, but maybe a bit surprisingly, because I decreased 2 values on the right hand side, but the actual volume is higher on the right hand side, yeah. But that's not really the end of the problem, because well, this is not really part of like ideal pi, yeah, like mathematical pi, yeah. It's sweet pi, and also, you know, we're measuring some values. Well, if we're measuring some values, then there's gonna be error that will depend on our measurement tools, basically. So we will have some error. And okay, if I have like values to 1 digit, then well, I cannot go. If my ruler has only one digit precision, then I cannot get a better estimate than 1 digit. And even this, yeah, if I'm measuring cake, maybe, you know, I will make my ruler dirty from cake or whatever reason. It can be even less precise. So if we take this into account, then we can calculate actual confidence intervals, or confidence regions in this case, for the volume, because it's getting like more dimensions. So so basically, our value is within some range. And what's more, if we assume that this is not really that I will always get this precision, it's only, you know, like sometimes, you know, maybe, you know, I measure and I'm completely wrong because of whatever reason. Then if we're going to more dimensions, so we calculate region, then our confidence region is getting smaller with increasing dimensions, because I'm raising things to the power. So I'm raising the value that is less than 1, to the power. So actually, like, our results are not certain and are within ranges. And now we can plot those confidence regions. I plot them as they are. So these are 86%, assuming that my ruler is giving 95% times like the value within this region. So now if we look at this picture, then can we really say that the second one from the pure calculation is bigger? Can we? Well, maybe. Maybe yes, maybe no. But it's clear that we are very uncertain about this. So maybe we need to measure more, or maybe that's just small volume. So maybe we don't bother. Like, whichever cake is good. Yeah? Like if I eat like a bit less cake, then nothing happens. Yeah. So that's coming to basically the few principal problems with evaluating any, you know, like any statistical hypothesis, really, and especially one about mean. So the framework is basically that I have something on one side and something on the other side. So it can be, I have a group of people before treatment and then a group of people after treatment. Or I have two cakes, or two similar things that differs in some way, and I want to say which one is bigger, better, different. So there are two aspects of this. That the one thing can be bigger, and it can be statistically significant. So it can be statistically bigger, but not necessarily to the level that we would care. So if we have a marginal increase something, it may be statistically significant because we gathered enough data or whatever or whatever other reason, or basically it's just because we did experiment long enough, so we got statistical significance. But it's actually pointless because this is not really effect that we would consider as practically important for us. So that's the whole point really of the first part of the book, is really to think about anything you measuring in statistics or as the effect, as the measuring effect. So we're interested not whether our results is statistically significant, but in the first place whether it's practically important, whether this is really change. Okay, it can be change that is not by chance, but if we have the test that is powerful enough, then we will always be able to detect some change because we did something to our sample. So it's like treatment, or we cut those cakes differently, so they're going to be slightly different. So if I measure them precisely enough, I will always find the difference. But that's maybe not something that I would care really. So so at first we're looking at size effect. So effect. So we're interested in increasing by some value. We want to improve by 5% or by 2%, and then we're interested whether this improvement is significant. So that's the general framework. That's the general idea. And now, after this introducing all the concepts in general, we're gonna go into some details and actually some examples how to apply like statistics for real data. So we're going to look at something called t-tests. Anybody familiar with t-tests? Have you heard about something like t-tests?
There's the chi-square test with the right.
Chi-square test, yeah, that's a bit different thing. Okay, that's yeah. So I introduced t-tests. It's a good occasion because it's a fairly popular test in social sciences, especially. I guess because of simplicity and because it's actually testing. It's for testing means from normal distributions. Then we look at a few examples, which one is copied from my thesis to show t-tests. And then we mention some applications, and I'm going to actually show the application for items ordering for online stuff. Yeah. So let's introduce t-test. So as I said, we have two populations or two things. We have some mean value, and we want to say whether it's changed or stayed the same. So what's the procedure? It's normally you should ensure that our measurements comes from normal distribution, which is it's a bit tricky bit because sometimes you can have usually for t-test it's basically ensuring that there is no the data don't have like two peaks, for example, because then that's clearly not normal. In online stuff, that would possibly mean that somebody is cheating or like trying to cheat the ratings for the items. So usually those data, they will be fairly normal, and even if sometimes they look a bit like even if they look something like this, and it's not many of them, that's fairly normal. That's such as there are tests for normality, and usually if we're talking about means, then if we go to huge sample, so if we're measuring height or size of the pie, if we don't get normality, then or fairly normal data, then that means that somebody is, misunderstood how to use the ruler or something like this. That's basically. So somebody did something, something stupid in measurements, so they are skewed. But it's all the assumptions is about normality of data. Then we calculate the mean estimate. So basically we sum over all the samples, all the measurements, and divide by number of them. And if we calculate standard deviations, then we can already have confidence intervals, as I shown in the picture that I shown in the beginning. I'm not going to bring formulas. There will be enough formulas for items ordering. And then we calculate something called t-statistics, which is so already here we know about size of effect already here. The second part is just check whether it's significant, so whether we actually can say something about our hypothesis. So this is why we need this t-statistics, which I introduce here. So for t-tests and for mean testing, we can have two main cases basically: paired data and unpaired data. Unpaired data is basically we have some population, we do something to this population, or I don't know, it's like voting tendencies, or like 2 weeks before election and then week before election. Yeah. So we of course we have different people, like in the second survey. Then we deal with unpaired tests. And then there are like two kinds of tests. So this is like formulas for this t-statistics. They're similar, but I wouldn't worry too much about them. And then we have something called paired t-test. So when the data are paired, so we have we're taking the same measurements from the same people. So we have control group that we check without treatment, and then we add treatment, and we check what happens after. So this sort of scenario. And I'm going to actually show some examples of those, of actually performing those t-tests. So one example is from my research. So basically, I had in my research, I had few tables like this. But what's interesting about this one? It's comparing two compression methods, because this was what I was doing for the research. It's basically changing one parameter in the method, which is dictionary. Well, I'm not going to go into the depths of the actual research I did, but it's basically I have one method of compression and second method of compression, and this one was basically doing some training, some evolution of some model, and this was, well, not quite random, but we can say like without the model. Yeah? So I wanted to know whether my model actually helped, improved compression. So I had a few images, and yeah, I got some results. And then I did the whole procedure. So I got the confidence interval for mean difference between those numbers. and I saw that it's actually it's fairly big, because this is standard deviation for the difference, and I got 0.34. So the ratio of no, sorry. Yeah, the ratio of change of the actual deviation comparing to the mean is showing me like how strong is how much I the mean to the deviation is showing me how much I actually improved. And if it's much more than a standard deviation, I end up with like fairly good separation of my mean. So my new mean. So that's my first mean, and that's after training. So if I'm much higher than standard deviation, then it means that the effect is big. So it came out it's significant, and what's more, it's only 10 samples. So if the effect is so big that actually you improve so much, then 10 samples and that's enough. And even that's why I said it's worth reading this book before, because I could have had just 6 samples to also get significance for that big effect, which is quite interesting, because that's sometimes experiments are expensive. So if I'm expecting something big to happen from my experiment, then why to get 1,000 people to do experiment when I can do on 10? But that's not that common really. It's a bit extreme example, but in this case, indeed, six samples will be enough to get significance. Okay. Then another example was the comparison of fuel consumptions for cars in US and Japan, and that's unpaired test. They had only 79 samples, 79 measurements from Japan and much more from States. And yeah, from data it was expected that actually US is much higher. I'm not showing the raw data because it's a few samples. And the same procedure. It's only with unpaired tests. You can imagine it's a bit more difficult sometimes because you have different sample sizes. So you're not always gonna get significance that easily. It's much more tricky. So then the sample sizes, even for big effects, they should be fairly big to detect it. So okay, that's about t-tests, and we're gonna use some of these concepts, like especially confidence intervals, which is the core really topic of this talk. So now let's come to the last problem, the problem of rating items, and show how t-statistics, because this is what's going to be useful, how they're going to be used in this problem. So we have our rating problem, and basically I consider this in two sort of ideas, two frameworks. One is that users can just give positive and negative results, and other is actual rating on the scale. In practice, I'm going to show only this example and apply the idea from this one to the rating one. So they're like old good solution that you would just okay, if I need quickly to do something, then okay, I just order by average rating, and it's not bad. But or in case of what positive, negative, I can just get the difference between positives and negatives and also order this. The problem starts is when actually I have something like few thousand items, and their average rating is 4.97. So there is some well-established business with good products, but it was some nasty guy from competition who did bad review there. And this business is going to be always, below the guy who had one fiver from a friend or family. That's a bit. That's extreme case, but that's what's going to happen. So we can imagine that that's this average rating. That's maybe not ideal. But we have our sample, yes, our sample. So coming to the previous examples, we have our reviews. So those 10,000 or 1. We can calculate their mean, their average. We can calculate their standard deviation. So we could, and we have a sample number of them. So we could apply some of the stuff like t-statistics or confidence interval. It's similar problem. So how we can do this? So I'm going to show a couple of ideas how to do this, and I'm going to say like that they are not disadvantages free. So it's a bit more complicated. It's actually quite complicated problem. So the first ideas are for positive negative rating. If we have just positive negative ratings, then they come from Bernoulli distribution, so it's 0, 1 basically trial. And there are basically two ways of like basic ways, I would say, to sort them. So we're not going to sort by average, but we're going to sort by lower bound of our confidence interval. So if in the case of our guy who has only 1 rating, the confidence interval is going to be something like this, because we have just 1 sample. While for our guy that has 10,000 ratings, it's going to be something like this. So this guy will be lower than this guy if we look at the lower bound of confidence interval. So you can have feeling that that's a bit like hacking. But this is what people are doing, and it gives we shall see some results. And there are like some ideas from statistics, like there are formulas basically for how to calculate it. Yeah. And I see that it's type 1. Okay, there are some more sophisticated ones. For continuous ratings, we can use our t-test, or what's called our t-statistics for confidence interval estimation. So similar estimation as in the examples with hypothesis testing. Or which is more practical, use approximation of this called z-statistics. But in this case, using this actually doesn't solve the problem of 1 or 2 items, because we need standard deviation. If you have 1 item, or all items are rated by 5, then standard deviation is 0. So we still just stuck to min. So what people doing, and I saw, there are actually people, they are doing this with this sort of like rating systems. They add some constant to they scale basically. So if there's only few fives here, then they're gonna be scaled down. But when the n increases, so we have bigger sample, it's closer to the actual value of this statistics. So what I'm gonna do, I run a bit of experiments on the test set that we've been using for this Kaggle challenge, and I want to basically show you what kind of orderings I get. So yeah, the picture just by averaging is something like this. So we got our items with all fivers from family and friends on very top of the list. That's just by average. Then if we order them by the number of positives, I think this is like by the ratio of positives, it is a bit it's actually getting a bit better, but still fairly small numbers on top. That's just positives are above 3 and negatives are below 3. So I'm actually flattening the problem to 0-1 problem from rating problem, to use the concepts from this 0-1. Then this one is by the difference. This one is difference between positives and negatives, which looks a bit better. So here we actually get the ones with a lot of reviews and with high confidence about them a bit higher. But I would say that a lot of not so good on average guys are getting to top. We're just getting the difference between positives and negatives. So that's not really. It doesn't seem to be really that good. Then we have our z value. Is it by z value? That sounds a bit. That sounds much better, really. But still, I don't like those guys with fairly low averages. Is it? Yeah. Ah, okay. That's z value, but with the streak. But I used quite high value of 50. So then I got reasonable ratings up. But then the problem is that I'm actually, if the guy has 1 or 2 ratings of 5, then and the other guy has millions of ratings of 1, or a lot of ratings of 1, so it's basically rubbish. Mm-hmm. And this guy is starting and has just 2 ratings of 2. So if I scale him by this, and he has only 2 ratings, so you can imagine, like, if I put N2, it's doing something like this against his fiver. So he's going to be much below the guy who has average 1 from. So that's the problem with this sort of scaling. And people are doing this trick. So they are basically, in this way, they are basically putting all the guys below some threshold, like to the very last or like very end of the list. So that's not ideal, really. And if I put 0.5 here to this, it's actually I'm coming back to the same problem that was before, because it just doesn't change it enough. And I didn't run this one. Okay, because I changed. Yeah, this one was the same sort of problem. That's it's okay, it's more sophisticated, but again, it's a problem with the small guys. So they should be either treated differently if I want to use those methods. They will start working like above something like 30 or 30 samples where I can assume normality everywhere. But interesting is our Wilson method. So this longest formula. I don't know you recall the longest formula. And the longest formula actually it's quite interesting because it's actually giving fairly highly rated guys and with a fair amount of ratings on top of the list. So I like this sort of the result of this method because it by all those additional terms it takes into account all those like most obvious problems with rating. The advantages it flattens into splitting into it's has to with Bernoulli distribution. So I'm ignoring whether it's 4 or 5. Yeah, I'm treating it as a good rating, which is maybe good, maybe bad. So it's if I want to use this is how I would do this. So yeah, that's basically the last example.
You couldn't easily extend if that was a rating of say 1 to 10. That couldn't be easily extended because then you're saying 6 is the same as 10. Which is big.
That's then you need to do something like use the normal ones for the bigger where you have more data and smaller one for smaller data for like different formulas. This is what people are also doing. But and again, this advantage of doing this is you have to have this threshold. So you will have some strange things happening around this threshold.
Yeah.
And
you extra vote when you drop down.
Yeah. You got extra vote and you drop. Yeah, exactly. Yeah, and this will be happening. Yeah, it's maybe not that often, but it will be happening.
Presumably, a lot of it comes down to where you choose your threshold. You'd have to, there'll be better points to.
But it may also depend on the type of business you're doing, on the global average for your type of reviews. And
you can take an average of different algorithms as well and blend algorithms, can't you?
You could blend, yes. But I will actually mention something in the conclusion. This is, I think, what Yelp and Reddit is doing. I think so. I cannot, give my hand that this is exactly what they're doing. But they're doing something like
similar
with Wilson confidence intervals. So I think Amazon also introduced something because they were using always, I think just average rating. So, but I think this one is definitely this one is being used. So so basically, we have this like long tail problem. So the problem with those guys that has very few ratings. So we are very uncertain about the mean rating. I shown that there are fairly simple ways of just trying those ratings and implementing it, even if in a real system it's just change your query that gives ratings and with plugging some statistics. And even sometimes you possibly can plug just function into output of it.
Yeah, when you give an example, I thought it was quite neat. You can just try them out just as a straight query, just to, as you figure it out.
To see figure out. Yeah, exactly. It's quite good. And you can see what's happening and then export the results and play with them. It actually gives a bit better ratings. And then if you play with this, then you can also maybe try to achieve something special for your what you're giving to your user. Yeah, but
Mhm.
you want to influence them in some way by, or you want, or somebody pays more, so you want to promote him. You
Yeah.
can also add those things,
Yeah.
and just in the in simple SQL. The thing like with all the problems that there are people trying the methods that are more robust to all those problems with thresholding. So basically, they adapt to the new ratings basically. So they update so you have like some model of ratings, and then the new ratings are coming, and the model updates itself after each new rating. So in like within the Bayesian framework, but that's out of the scope of today. But I'm actually planning to bring some Bayesian experts from. I'm not one. It's a shame, to be honest, because the group that Aston, that's my supervisor, is from there, like experts. So that's possibly the solution to many of those problems. Just to have a model that updates, but then we're not anymore on simple SQL.
No, it's a lot more work involved. Yeah.
You need this model there somehow to be in your system. Okay, yeah. So that's basically it. Thanks. And any additional queries, thoughts?
Is that the book that you were?
Yeah, that's the book about effect sizes. But the examples are from just from some blogs and web pages. I should possibly put into the presentation somewhere the list of couple of blogs that I put the link to the example. I took it from some undergraduate course, statistics. And then there are like a few blogs that they're looking at this. Yeah.
Thank you.